Hello, thank you for joining us. My name is Ildefonso Polo, Director of VP of Product Marketing for VX, and I'm going to be talking today a little bit of some topics that are important for timing measurements in the field and comparing to with the information that is available in webinars and documentation available today from the internet. So we're going to be talking, seeing that synchronization is not as complicated that it may be presented to many people or by many people. A little bit of an overview of PTP because I'm going to need it for some of the examples that I'm going to present. Where the idea here is to talk about real problems that you can face in the field and that you need to be aware of, and so your process takes them into account. And so we're gonna go talk about the challenges, the realities, and perhaps give you some practical advice that you may take or you may leave. The goals is give you just a brief introduction of the PTP for those who are new. And again, we're trying here to talk about practicality, so things that you can act on. So you may be doing a lot of measurements, or you're reading documents or getting webinars that tells you that you have to measure all these things, and maybe only a few of them give you real actionable information. And the idea here is to create that, get that conversation going. So I'm going to give you, from my professional and personal point of view, my experience, a couple of topics. This is a very long list of topics, but I'm going to be talking just about a couple of topics that may help you, discuss and question what you're doing today. Hopefully, I hope that we give you something that can help you improve the process. So sometimes when we go from the lab to the field engineers or field technicians, we get these new people into new technologies, and they start seeing all these acronyms and all these definitions and all these parameters, and especially synchronization and network timing seems daunting from the beginning. But it doesn't have to be. A lot of these parameters that you see on the screen were, fashionable some time ago at the beginning of the definition or the implementation of PTP for telecommunications. So some of them were used during the R&D process, during the initial evaluation process, in which service providers and network equipment manufacturers work together to improve the system in general. So they all had their times, and today, if we are going to just deploy PTP, perhaps we need to focus only in the ones that really give us information, actionable information. So why are we doing this? You may have noticed that you probably have gotten invites for probably 5 or 10 synchronization presentations or webinars in the past few months. I had. So I attended some of them, and I still see the same message. It's just a very high level message talking about PTP, and this is it, and you need to do this and do that, but it doesn't tell you how, why, and what information you're getting from it. So the idea, I thought we have to bring this down to a more practical approach. And the problem is that there are so many things we could talk about. So I only had to pick a couple of them that I think they are very important, and I think they're on most of the time an oversight, and people are not aware of them, and they could affect your measurements in the field. And I'm, again, going to focus a lot on measurements, but I'm going to give example based on the PTP protocol. So the basic concept of why this is so with, or why this seems complicated is because every time people go to webinars or attend workshops or seminars in synchronization, they learn, they hear all these concepts and acronyms and things that need to be done, but they address a wider audience, and more specifically R&D and evaluation labs. So when people come back or from one of these events, they usually have a lot of questions. We get a lot of calls from people saying, hey, can you do this? Can you measure that? And the question back is, I mean, is that important to you? For example, these days we're getting a lot of questions about measuring Class D devices, just because it's a hot topic in the R&D evaluation lab community. So people that are in charge of deploying PTP are starting to ask the questions, and maybe they don't know when the Class D devices will come into play. There is also a little bit of bad marketing. We as a test equipment manufacturers in general benefit when people are afraid of the technology, or they don't think the technology is reliable. So trying to imply that you're going to have problem with the technology sometimes is used as a tactic to, get you to buy test equipment. This is not the case in this particular. I hope this is not the case in this particular presentation we're doing today. And also we have evaluation labs. Evaluation labs in the telephone companies or in the any company that are early on or in the front end of the technology, they usually get exposed to new technologies. They get to test them. They get to interact with the vendors, improve the products, improve the services, and then they become the expert. They become very knowledgeable. And of course, if I'm going to start deploying the technology, they are the ones who get asked, what do we need to do to deploy PTP, for example, synchronization using PTP. And the problem is that sometimes they project their needs into the field, and we get a very complicated request or configuration for products with a lot of features included that may not be useful in the field. Some of them are for information only, some of them are not actionable. That means that if you see this problem, what can I do to improve my service or improve my network? And that, I think, is the goal for test and measurement or field verification of any technology. And of course, there are some myth, theories, opinions, and interests that always keep going around. There is also, in terms of the bad marketing, I think we hear a lot of things. I've attended a couple of those webinars, and they have mentioned things like you can do a very quick time error measurement. So we can do it quicker than anybody else. So what does it mean? Of course, we can do the measurement very quick, but are we telling our users what are the caveats of that? There are trade-offs, especially when we're talking about high precision. Also, intimidation a little bit. One of the quotes that I kind of like, I saw in one of those, is that timing issues are on the rise and it will only get worse. So with that message, what else can you do? You need to be prepared. You need to start running around, I guess, to figure out how to fix all these potential problems. So if I were to create a presentation of a marketing webinar for PTP timing measurements, I will just give you one slide, and this is the slide. And I will tell you that you have to measure time error somewhere around those points. And I will not give you the details, but I tell you that you have to do it somewhere around here. And the details are going to be left out of the presentation. And I'm also going to tell you that there are limits that you have to meet. And that will be it. Then my presentation is done. So hopefully I'm not going to do that today. And you're going to, again, hear a little bit about my personal professional experience. I'm going to tell you what I think could be important, what I think people are sometimes not paying too much attention. And it has nothing to do with the specific products. So we're not going to be talking about the specific products here. We're going to be talking about things that hopefully will make you question what you're doing, make you think, opens a conversation. And if you think that information we provided is valuable, then you feel free not to use it. But we just want to share a little bit of our experience. So before we get into those points, let's see what's new with PTP. Most of the time we refer to PTP version 2, which is the version that we're all using. But we're actually in what people call today PTP version 2.1 or 1588 to 2019. It introduces a few changes that doesn't really affect the current network or the current deployments. The current deployments are most likely all PTP version 2 compliant. And what it does, it prepares PTP to be improved. So we're going to be seeing these being developed over the next few years. For example, it provides the means for a better interworking between the packet clock and the physical clock. So if we have PTP and sync key, now the two clocks can work better together and actually improve the precision and the reliability of the system. It also opens up other few things for security improvements and also to allow to work with other industries or other applications. So it is mainly just opening the door to do more with PTP. There is, I mentioned the questions about the Class D and Class C devices. That's a very common question these days because, again, webinars and workshops are talking a lot about them. So I could just summarize it that there are limits that need to be met by the devices, and they have to be measured for sure. And one thing that it is important is that those limits are very, very narrow, are very, very small. So these devices are should be very, very high precision. So the challenge here is how are we going to measure 5 nanoseconds? Luckily, a lot of these will be done in the lab with a control environment where you know your reference, you can verify your reference, you can do a lot of cross checks, and you will use probably a lab type equipment to do Class D type measurements. And the other part that we may talk about later and we'll mention later is the filtering. So we don't use for some of these the direct measurement. What we do is we use digital filtering to smooth out the measurements, and we'll touch about that in a little bit. So let's talk about the packet-oriented timing measurements. That means we're going to be measuring or assessing time error based on the protocol and the timing of those packets. But before, we need to get into a little bit into the language. So we hear about a lot of precision oscillators, precision timing, precision time protocol. But we need to figure out, I'm gonna be saying some of those words, and I don't have the absolute definition, but this is the definition I use for precision. And I provide it to you not because this is the right definition, I provide it to you because I'm going to be talking about it and you need to know what I'm trying to say or imply. To me, precision is a combination of the best of all of the above. So if you have a precision device or a precision instrument or a precision generator, I would assume that is highly accurate. That means low error and very small uncertainty or very high resolution. and it is repeatable. That means that it's stable. If I take a measurement now and I take it again and take it again, um, the measurement is the same. Or if I'm generating a signal, the signal is always the same. Same reliability is another factor that I consider. Highly reliable precision requires highly reliable systems. What happens is if I turn it off and turn it back on, do I get the same measurement? Do I generate the same signal? So you cannot have one of those and be precision. You need to have all of them. So each individual one by themselves is not, you can have very high resolution, but that doesn't mean that you have a good accuracy. So for this type of slides, most of the time people are using the target analogy with the bullets, whether they are to the left or to the center, spread around. I prefer to go with a crazy contrarian example. So we all remember the first generations of Volkswagen Bug. The steering wheel of that car was kind of wobbly. You have to kind of keep on going left and right to keep the car going straight. So it was not a very stable car. It was not a very stable steering system or accurate steering system. So some people say, as an example, this car was bad, but it was always the same bad. That means that it was reliable because it was predictable. You already know how it will react to certain things. So if you already know, you can correct it. And that's one example, the counter example of not having one thing and having another thing. So that's what I mean by precision, is having the best of all of the above. The other part about that conversation is that we see a lot of confusion between resolution and accuracy. Resolution is what we present on the screen, or what we can actually measure, the quantization. That's the physical resolution. And accuracy is how good that measurement, how true that measurement is, for example. So one quick example is when we measure time. So we measure every second. If I'm comparing two 1 second pulses, and I have an accuracy of 1 nanosecond and another resolution of 1 nanosecond for this example, I will get raw measurements, direct measurements like the ones I'm showing right here. If I have to apply some math to that information, then the things are starting to get a little bit blurred. For example, if I need to do a rolling average of the last two measurements, I will get a resolution of 0.5, plus or minus 0.5. If I do it with the last four measurements, then I will have 0.025, plus or minus 0.25. So if I keep on dividing, for example, that's one of the math calculations that we can do, and that will create more and more significant digits. Does it mean that when I do that, my accuracy increases, or my accuracy is still 1 nanosecond? So those are some of the questions that we need to ask ourselves, is what we're seeing on the screen is a direct measurement, or is just a calculation based on some physical measurements? So I mentioned this because in PTP we use filtering, and filtering is quite similar to doing average. So if we average 70 measurements, then we will get a lot of significant digits from the calculation. That doesn't mean that those digits are useful for what we're trying to do. So we will need to differentiate what we're seeing on the screen and not confuse it with the actual accuracy of the device. So there are two things that when we do synchronization verification for the field in our case is to measure the physical clock, and that is my area, the area that I really prefer, is to compare the actual output of the clock with a reference and actually measure the phase difference, the time difference between the two. That is a direct measurement. Or the one that is now becoming very popular, which is the packet-based TE calculations. So in this case, I'm going to be using the packets and the timestamps from those packets, arrival and departure, to calculate what the TE would be for that system. I prefer the first one, but since the second one is becoming very, very popular, my examples here are going to focus on packet-based time error calculations. So from the instrumentation point of view, for the test and measurement point of view, when we do these measurements, we don't use the actual slave clock. We basically replace it with an emulation of the slave clock. So that's why you will see that they are referred to as quasi-slave or pseudo-slave or any other name, that reflect that it is not the actual device, but an emulation. The other part that we need to understand or remember, sometimes we forget, is that the GNSS, or like some people call it GPS, and reference clocks, they are allowed to have some error. They are not perfect. So there are some allowances, and that we need to figure that out and keep that in mind, because sometimes the main thing that we find is that two measurements are slightly different, and the question is, why are they different? Why the two measurements are not exactly the same? And that could be part of it. So there are those real life limitations. So what can we do? Basically, just be mindful, know what the limitations are, whether they are these ones or some other ones that we're going to mention in a minute. So just make sure that you understand what affects your measurements and put that into your procedures, and into training your field technicians, your field engineers, get the training so they understand where they need to be careful to minimize any errors in the measurement. So for those who are very familiar with PTP, don't get discouraged by this slide. I'm using the ladder diagram for those who are not very familiar, but for those who are familiar, I will continue to use this in my examples. So that's why I bring it up here. So when you turn on a slave clock, I'm not talking right now about a test and measurement equipment. I'm just talking the actual network element, the slave clock. When you turn it on, it doesn't know time. So we'll just pick whatever time somebody put in as a default. So when you turn it on, it is inaccurate. So the first thing it will do is establish a connection with the master, and the master sends the sync message with a timestamp of T1. When the message arrives to the slave, it's timestamped again as T2. If the master doesn't have the processing power to send the timestamp within the sync, it will just send a secondary message, the follow-up, and either way, we get the T1 timestamp from the master. Sometime later, the slave will send a delay request packet and keep record of the timestamp, T3, and the master will measure the time of arrival of that message, and sometime later will send the reply back. So once the slave have all that information, all he has to do is apply this formula, and voila, you get, in this example, 150 is your error. So all it has to do is remove 150 from the current time and get the time sync. That's the pure theory of it. So it assumes that the forward and reverse delay are the same. But what happens if they are not? So if they are not, basically, if we have a 50 nanosecond asymmetry with the forward being longer than the
asymmetry is the absence of or a violation of symmetry. Symmetry is an important property of both physical and abstract systems, and it may be displayed in precise terms or in more aesthetic terms.
Sorry, I forgot that Siri was
Would you like
paying
to hear
attention.
More?
Sorry about that. So if we have an asymmetry of 50, it would produce a time error of 25. That will be, again, indicates if it is in the forward, then it will delay the pulse. That means that the pulse of the slave will come out a little bit later. And if the delay is larger on the return or the reverse, then it will create a positive time error, which is half of the asymmetry. And that means that the pulse coming out of the slaves will be a little bit earlier. Not just the pulse, but the time will start earlier. The second will start earlier in the slave, because it's not always a physical, it could be a function of a device, an integrated function of a device. So these are the basic things that we're going to be looking at as a theoretical calculations and the formula, applying the same formula. But in reality, there is packet delay variation, there is noise, there is a lot of things. So the packets don't always arrive at the same, with the same delay, and that creates a variation that we separate normally in a constant component and a variable component. So do we have to worry? Not really, because the slave clocks devices, the network elements, know how to deal with it. And they have been engineered to do this job and figure out what the most accurate time is based on a statistical analysis of that information and all the packets that go back and forth. So here is where things get a little bit complicated. I always call it the asymmetry. If you're doing a measurements and you see that behavior, that you have a 50 nanosecond or a 25 nanosecond error, for example, is it asymmetry or is it something else? So for ones, PTP networks are fairly new and they tend to ride in a very well-engineered networks. So I always wonder how common is asymmetry these days. The information is not widely available, so that's part of the not having reports and how often you find asymmetry is a problem in networks that you're testing. And the other thing is that since the reference clocks can have error, then that can, if you measure with one of those being in error, it can look like asymmetry from the test and measurement point of view. So you don't know whether it's a real asymmetry or you may have a difference in reference clock, for example. So there are many possible causes of asymmetry. They can be at the core, at the very center of the network. The nodes themselves the switches and routers and boundary clocks can actually create asymmetry, static and sometimes variable, depending on the conditions. From the links, the physical links themselves, that tends to translate into more a constant time error. And believe it or not, the test equipment could show you something that looks like asymmetry, but it may not be. And just because it's a GNSS receiver where it gets the timing from is a little bit off, because it's allowed to be off. And in reality, there are going to be multiple GNSS will have a little bit of difference between them. Cable delay compensation is one of the possible problems that cause behavior that look like asymmetry. So we see a little bit in all these lists the word cable. So again, we're going to mention this, and compensating for cables is very, very important if you want to have a very accurate measurements. And this is one of the points that I want to stress during this presentation. Is a little thing, but it can make a big difference. So before I show a little bit what happens in the field, I'm gonna take it to that core of the network. If I go to the lab or the core of the network, and I need to verify the time error from the packet point of view at the grandmaster site, I normally will use a very short fiber cable to connect to the master, a cable that I know, a duplex cable that I know is symmetrical. I will use the same reference clock from the master. So there is very little room for error here. Since both have the same time reference, I can make a very accurate measurements and very predictable measurements most of the time. And again, I apply and this time I apply the master time transfer error formula, which is very simple. That measures the time error in one direction, the time error in the other direction, assuming that there is no cable delay. But here we will have a little bit of cable delay using a 6-feet cable or a 2-meter cable, for example. It is symmetrical, so it will just not be seen in the results. So we have to be careful. Is just that we remove the delays from all the cables that we use, and we remove them correctly. So when we see this particular diagram here, the graph, if I'm connected to the grandmaster and I have in the same reference clock in the instrument, some people say that, yeah, we are measuring the grandmaster. But in reality, we're not measuring the grandmaster. We're measuring the whole system. We are measuring the error from the PRTC, the reference clock, which is tied to the error from the satellite system, which is also includes the error in my introduced by the cable, the reference cable, and the error of the instrument itself. So it's not just the grandmaster, it's all the errors get accumulated and we get one result. It's not really easy unless you have all the tools at hand to differentiate what contributions come from where. So that's one reality. We always measure the whole system, including the instrument itself. So any inaccuracies anywhere or any delays anywhere can cause a problem. Or not a problem, will cause a deviation in the measurement values. So one part that is when we move to the field, far from the lab or the node or the core of the network, is that in many cases, the slave clock is not a separate device, it's a function integrated within the edge device, whether it's the antenna, whatever the application is, it may be integrated and it may not give out any indication of how good it is or that we can measure it. So in some cases, we have to remove part of the elements of the network in order to do some measurements. So we are not testing the link as it will be in production. We will just verifying that it should work under the certain the given conditions. So if I take again the same approach with the same formula, which I'm going to go through different iterations of this formula here, or with different values for that formula, if we assume that the tester and the grandmaster have the same time, there is no error whatsoever, then the measurement should be 0. So if everything is correct, then we should have a time error of 0. But if we don't have access to the reference clock, for example, the slave clocks may have a built-in GNSS receiver and an oscillator, a precision oscillator inside. So we don't have access to that oscillator or that GNSS receiver. So we may need to use another one, a separate one, whether it's from the site where we are in, or if we're in a lab, for example, or we have to use a complete separate one with its own satellite receiver and with its own oscillator. So the second example here shows the worst case scenario given the allowance that I have. So for a PRTC, I'm allowed to be plus or minus 100 nanoseconds. That is big, that is huge for today's standards, but that is the value. The new specifications talk about 30 nanoseconds, but this is what we go for with traditional reference clocks. So if I take that to extreme, like I have the atomic time as my reference, and I say that the grandmaster is minus 100 inaccurate, and the test set is plus 200 inaccurate, then and I have a 200 inaccuracy in the system, that will show in my calculations. So in reality, the grandmaster or the PRTC1 or the PRTC2 are not going to be that far. Technology has gotten a lot better in terms of GNSS receivers. So we can see today numbers are smaller, but you can still see numbers in the 20 nanosecond, plus or minus 20 nanoseconds, for example. If you are using the latest technology in GNSS receivers, maybe you get lower numbers, but they are numbers that you will see significant effect between whatever reference is used for the grandmaster and whatever reference you're using for the tester. So there may be some difference in the measurements, and you need to account for that because there are things that are out of our control. So the other thing that I want to show, I guess I'm going to just plot this over time, because I mentioned before we have PDV, the packets don't always arrive at the same time or have the same delay. So we don't say we have an error of the forward time error of 10 nanoseconds or a forward time error of minus 10 nanoseconds. We say we have a time error of around 10 nanoseconds, and then we do a lot of analysis to come up with values that are more constant for us. So we use normally the CTE, the constant time error, which means that we're going to average a lot of those values for a long amount of time and come up with the most likely constant component from all those measurements. And from that, we can get the time error, the dynamic time error, which is the noise, the PDV, and all the variable stuff will be part of that. So if you have a perfect system, this is what it should look like. The distance between the green line or the green wave and the orange and the yellow should be the same, and it should be balanced and set to 0, ideally. If we have a longer delay here in the cable or in the system, then these just move apart a little bit. So if we have a longer delay, then the traces just move apart with the delay that they are measuring or the time error they're measuring. So we continue to use the same type of formula. Now, having this forward and reverse being symmetrical to the green line, the green wave, does it mean symmetry? Not necessarily. Symmetry is measured against 0. If we know that that the measurements are correct. The green line, since we're dividing by 2, the green line will always be in between, in the middle of the reverse time error and the forward time error. So that should not change. If the test set, for example, is plus 20 nanoseconds off, then the results will be minus 20 nanoseconds off. So it will be kind of the reverse effect. In this case, we will see something like the reverse time error being negative. That could be an indication of a problem. But most of the time, we're not dealing with these small delays that I'm using in this example. If the delay is bigger, this signal will be probably here or above, so we will not see that it is a negative number. Same thing happens if the instrument reference is minus 20 nanoseconds off. Then the result will show an error of plus 20. Here we're looking at these numbers and we can figure it out, and we're looking at these calculations. But when you're on the field, you have no access to none of this. You have access to this graph that give you probably a lot of information, but you don't have access to know which one is the one that is introducing error. Is it a true network error, or is an error based on the references that we're using? So here there is a lot of trust. You need to trust the procedure. You need to trust the vendor, and maybe do a lot of testing before the equipment gets to the field and people know what to expect from them. So if the error is on the reference that actually drive the grandmaster, and this is what we're trying to measure, if the grandmaster is accurate or not, and assuming that the tester is accurate, then a positive error on the grandmaster is measured correctly as a positive error and by the instrument, just by using the same formula. So if now we have real link asymmetry, in this case, we have different delays in one direction than in the other direction, then the error will be the difference, the half of the difference of those delays based on so a 10 nanosecond asymmetry would produce 5 nanosecond error, which is the real measurement. And the graphic still looks very similar to the other ones. So we need to be a little bit understanding what is going on. And this is exactly how asymmetry is measured. In this case, we're measuring against 0. That's where my DTE line is. And so we'll see that the forward is a little bit smaller than the reverse. So you get some information, but you don't have access to that left part of the screen. So that's what is important, that instruments give you as much information as possible, so you can figure out what could be happening in your particular case. So in the field, in the real life, what we're gonna see is a combination of all of the cases that I presented before. Error in the master, error in the instrument, some asymmetry in the link, and variability over time. GNS says receivers, especially the older ones, tend to change over time. They have day-night variations. They have temperature. There's temperature variation. There are variations due to traffic on the link. There are many factors that could make the delays change, and then you will not get a straight line. So you will get more noisy lines if you do the measurements over time. So if we take that same approach that we had at the central office, where we when we can actually qualify every single item that we're using, we can see that the signal coming out of the cable is accurate because we have other instruments that we can measure it with. When we are on the field, we have to rely only on the instrument and its reference. And its reference is going to be most likely a GNSS receiver and an atomic clock or a precision oscillator. So that is going to be the case. And now the question is, how good can you make that satellite signal be for the given conditions where you are? You can be indoors, you can be outdoors. Sometimes you get access to a roof antenna. That is the best case scenario. Sometimes you don't have access, so you need to figure out what is the strategy for every single of those scenarios. So it is a lot more complicated because there are more elements in between. So basically, we're removing the slave clock. We are emulating the slave clock. We connect with a very short cable to the boundary clock or whatever is available, whatever we're testing, and we do the test towards the grandmaster. So we still have the problem of that we're using two references that are independent. They can be different, and we use basically the same formula that we use here, but now you may find it referenced as a two-way time error. That's a very common name for the time transfer error formula. So if you search for it on the standard, you may find it difficult to find the two-way TE. So you may find the time transfer error formula, and you can study it a little bit more. So we have to keep it in mind that the time for at this side may be different than the time at this side, just because all these the receiver is allowed to have some error. Then the instrument will have its own accuracy. Calibration issues could be also a problem. So you're gonna get measurements that were designed. So we're gonna be using measurements that were mainly designed to be done here in a very controlled environment. And this is an environment where we have no control. So some people say, well, if I do have access to a 1 PPS signal, can I make a very accurate measurement? Well, if you have access to a 1 PPS signal that is accurate, stable, and high precision, then the question is, why did PTP got deployed to that site if the site already has an accurate signal? So most likely you're not going to find those cases in the field. So you have to rely on the GPS as a main traceable time source. And again, if you're using the latest generations of multi-band, multi-GNSS systems, you can get very, very low error from your GPS. But if you're using an older generation of GPS-only receivers or two satellite system receivers, then the error could be higher, and it could be significant, especially if we're talking about 10 nanoseconds, plus or minus 10 nanoseconds, and somebody's expecting to measure 30. That is a big significant contribution for that. The other part that goes back to my preference to measure 1 PPS directly if you have access to it. Whenever you have access to it, I will always recommend people to measure the actual time signal because we use a very well-known method to do those measurements. And we use a very accurate, reliable, high-precision clocks to define the sampling time. So, for example, for 1 PPS, we're going to be measuring the time error every second, maybe plus or minus 0.05 picoseconds. That's the variability that we have to do those measurements. So all these T's are almost the same exactly. And that is also a premise that is used for some of the calculations, that if the sampling time is regular and very accurate, then we can do certain analysis. For example, filtering, digital filtering assumes that this sampling is constant. But the problem is, as I mentioned before, not every place you will have access to the 1 PPS output. So if the slave clock has an output of 1 PPS, I would suggest that you use that one to verify the whole system, because it includes the actual slave clock that you're going to be deploying for that service. When we move to the packet world, then it gets a little bit blurry. So I mentioned from the ladder diagram before, we have the departure time of the sync message. We have the departure time of, well, it doesn't matter. We have a second message that could carry that timestamp, the T1 timestamp. Then we have the arrival time of the sync message at the slave. Then we have the departure time of the delay request going back to the master, and the master gets a message and then it responds with the delay response message sending the timestamp of the arrival of that message, of the original message. So once I have T1 and T2, I can calculate TE1, the forward time error. Once I have T3 and T4, I can calculate TE4. And when I have the forward time error and the reverse time error, I can actually calculate the packet-based time error. But when that measurement happened, where, here, when happened. So those things happen over a period of time, and we're individual events. And by the way, those events are not always in the same place. They are going to be wobbling left and right a little bit because there's PDB. So that is the question. But let's assume in this example that we use the sync message as my definition of the beginning of the sampling time. So we have a sampling time here. We do the calculations, and then we have one measurement. What happened the next time? One problem that we have with this approach, one problem that we have with this approach is that the sync message rate can be different to the delay request message rate. So we can have 16 sync messages per second, and we can have 8 delay request messages per second. So the second period, I will have my T1, the sync departure, and my T2, the sync arrival, but I don't have the T1, the T3 or T4. So I can calculate T1, but I cannot calculate the error because I'm missing some information. So what do I do? Then if you go to the standard, it will say, yeah, we'll leave that for further study. So that means that vendors could take different approach, how to fill this gap with information. So those are things when you're not just comparing the measurement itself, but you may be comparing the measurement you took with one product and the measurement that you took with another product. There is a slight possibility that the approach that they took to do the measurement, this measurement here is a little bit different. So if the sync rate and the delay request rate are the same, that is not a problem, but we still have a lot of events over time, and events that are changing that have different position every single time. So there is that question, how that affects what I'm measuring. Is it better to do it this way or to do it this way? As I said, sometimes you cannot do it this way because you don't have the 1 PPS output. But if you do, I suggest you use it because it's more reliable, like in my opinion. There is also the topic of doing measurements really quick, which is becoming very common these days. Everybody's talking about, yeah, we want to do a quick measurement, but there are things that you should not cut corners. You still need to get your equipment to be ready. Then if you are using GNSS, you're not using a PPS, a local PPS, you still need a GNSS to do a local survey, figure out the best location possible, the most accurate location that it can get before it goes into timing mode. Of course, if you put very loose values in the configuration of your GNSS, you can shorten this time. But that means that your uncertainty of the location is going to be bigger, and location is used to calculate time, so the uncertainty of your timing is going to be bigger too. So you need to figure out what works for you, what time do you have. We understand that people don't have all day to do measurements in the real world, but by experimentation perhaps, or by the scenario that you're working on or working with, you can probably experiment and figure out what is the best you can do. If you are returning to the same location multiple times, there is a shortcut that is very good, which is that you do the survey, location survey the first time. You do it a very good one. Spend a good 30 minutes, 1 hour, whatever the number is good for you, and then save the data. Next time, all you have to do is recall the data. If you recall the accurate data, you don't have to do the survey. You can just do the manual data entry, just recall it from a file, and go directly to the second part of getting ready, which is disciplining your oscillator. And here again, you can discipline it really quick, or you can take your time. The faster you discipline it, you are going to be cutting corners, and again, there will be consequences to that. So it is you need to figure out the trade-offs between all these points, and figure out what works for your particular environment, your particular network architecture, your particular application. The other part that is the last part is the actual testing time. So once your equipment gets ready, you know that it has accurate time and a stable time. It doesn't have to be just accurate, it has to be accurate and stable. Then it is up to you to decide what is the right amount of test time. You can do what I call a single shot, which is a very, very short time error measurement. But that just gives you an instance. It doesn't tell you how the system is working. It just tells you that right now, this is the time error. Time error can change over time. And if you are measuring and need to have CTE and DTE values, because that's what it is required for your report, then you have to wait at least if we use the number that people are throwing around this day, which is 1,000 seconds, so you will have to wait about 20 minutes to get the first result, because it will do an average of about 18 minutes of data before it gives you the CTE and DTE data. In reality, the standards talk about that 100 and 1,000 seconds sampling is for the lab temperature control environments. And if you're out in the field with uncontrolled environments, then we need to talk about 10,000 seconds. So about 3 hours of testing just to get the first sample. So again, I know that many people don't have 24 hours, 72 hours to do a good time error and stability testing for the system. But whatever time you have, you need to assess how are we going to do it, how are you going to make it repeatable, and what are you going to be taking care of to make sure you minimize any error during your measurement. And then you live with with that decision. So this is just a quick summary of the TE equals a constant part and a dynamic part. So if we go to the field to do testing, be prepared. That's the most important part. It's not just the instrument, it is the procedure, it is the test cables. People call me crazy, but my cables, they all have a label of what is the delay of each of my test cables. Measure the delay of the 1 PPS distribution cables if you are in the lab or in the central office and you have a distribution system for 1 PPS, you need to measure the delay for those cables so they can be compensated either at the source or at the destination. If you can, as I said, measure 1 PPS output instead of doing the packets. The challenges is how to get a traceable reference. There are places where you probably may not be able to get a traceable reference. So you need to be prepared for those cases. Some of the devices under test don't have a 1 PPS output. A lot of them do have it now, but it was kind of an afterthought, and they may provide it to you in a format that it may not be compatible with your equipment. And of course, the best results for timing and stability of precision timing systems is long-term. You are looking for stability, so you need to know what is the long-term behavior of the system. So we rely on GNSS for almost everything, even though there are many people who don't like the word GPS or GNSS, but we rely on them for everything on the field. There is nothing else for us available as a reference. The main issue is that a significant number of deployed network elements that have a reference clock, they may use all the receivers, whether it's just single GPS only receivers or single band dual constellation receivers. They are very common. If you bought one recently, you probably got a single band dual constellation receiver. They are better than GPS only, but there are better technologies today. Quad constellations, single band. But if the best technology available today for anyone is the multi-band quad constellation that is not only more accurate, more stable, but it has different sets of frequencies, so it is better with noise. So in metro environments, it will deal better with reflections and noise. So we have to rely on GNSS because it's most of the cases is the only thing available. And what we can do is minimize the possible, all the possible sources of error, whether it's a cable delay, a physical error that sometimes it's an oversight and we don't think about it. And that can be a huge problem in giving you inaccurate measurements. It's not the instrument, it could be the cable, for example. So the more information the instrument gives you, the better, because you are out there on your own with no way to verify what you're measuring. Some people talk about the holdover at the beginning of the 2000s when we were talking about PTP. Holdover was a dream to use holdover for inside measurements. You can do it, but it is not simple. You still need to practice a lot to do it. You need to avoid a few things. You need to understand that there is an uncertainty and it is not constant, so you cannot predict it, because if we could predict it, we would just compensate for it. So there are many things that if you're interested in using holdover, just figure out a process that works for you in your environment. For example, you may try to synchronize your instrument at the central office at 20 degrees Celsius and then go outside in winter and it's -4, or summer is at 35, so you will have one case of temperature shock. So holdover is mainly for systems that are stable, steady state in control environments, and it becomes very unpredictable when you take it to the field. Again, in some cases you will have to use it, but if you have to use it, you should probably learn a little bit more about it. There are a couple of videos out there. I'm not going to go into detail, but it is up to you to decide what is the process to get to the unit into sync and how to turn it into holdover. So important part of this presentation is the simple things can make the big difference. So I've seen a lot of problems with cables. So the signal can leave the reference clock very accurate at the port, but when it gets to the end of the other end of the cable, it's inaccurate, and that is given. There is nothing we can do about it. So all we need to know is what is the delay of every single cable that we use for our setup. So there are many ways to figure out the delays, and we have to use cable delay compensations. And you will see that in some instruments, there are many fields for cable delay compensations because you're trying to compensate for every single cable that you're using for your setup. One of the ways that we can do is if we only have access to one end of the cable is already installed. The only option we have is to use a TDR and measure the time of flight. The main problem with this is that most TDRs, even though they measure time very accurately, they don't give that information to anyone. They just keep it for themselves. And we'll talk about that in a bit. Or if you're in a lab and you have access to the both ends of the cable, you can use an oscilloscope to measure the actual delay of the system or the cable, or you can use other instruments to measure the delay of the cable. So you need to measure and document your cables. Again, people may call you crazy, but having all the cables with their own delay, to me, is very important. There is a few things that we take for granted. Sometimes we take a patch cord, BNC patch cord, and we say this is a 2-meter patch cord, and it's actually 6 feet patch cord. So where did that patch cord came from? US, Europe, China, we don't know. So it could be 6 feet and it could be 2 meter, and they are not the same. There is a big difference between the two. So my recommendation, just measure the delay and only focus on the delay. There is a small things that when we do calculations in our calculator or with a TDR, after we do a TDR measurement, is that there are some error based on the approximation of the speed of light, but that's a minimum, but it is there. We tend to use 300 million meters per second, for example, but the value is not exactly that. So there are things that contribute to those little errors, and if the cable is long enough, then they accumulate. So don't use delayed estimates, and TDRs will give you delayed estimates, not delay measurements, because they measure actual time. They convert it internally into using either the worst case, they use an internal table. The best case, you can enter the number from the data sheet of the cable, and it will give you a bit better distance or length. And then you have to manually use a calculator to figure out what is the delay. So if you can use a TDR that give you direct time measurements. So for example, a lot of time I see people grabbing a 6 feet cable and saying, oh, 1.5 nanosecond per foot, 6 feet cable, this is the delay, and you arrive close to 10 nanoseconds. And that's just a quick guess, a ballpark number that we normally, people use it during presentations, during training, because it's easy to say. People who are receiving that information may take it for granted. So that will give you a wrong measurements. So if you are using a TDR that gives you length, go to the datasheet, find the datasheet of the cable, and try to input the actual nominal or typical velocity of propagation to get a better result. In this case, the device gives you exactly the delay. and that's the preferred method. Find a TDR. They are not very expensive, so you can find them, and it's probably the best. You will get the best benefits from the little money that they cost. So here's an example of TDR giving you the measurements in feet and then in nanoseconds. So if we do the calculations based on the reading in feet and use a very accurate or a reliable data sheet, then I arrive to a delay of 137.5 nanoseconds, and the actual measurement is 133. So there is 5 nanoseconds right there of error. That 5 nanosecond will go into your measurement as an error to the measurement, contributing to that measurement. So in general, it doesn't have to be very complicated. It could be simple things that you can use to improve the success of making accurate measurement in the field. And the most important part, I think, is that you need to identify actionable information. So what are the data that actually give you information that you can act on? So those are measurement parameters, procedures that give you information that help you resolve the problem or improve the network. If you get a parameter that doesn't tell you nothing, then the question is, why are you measuring it? Is it for the record? Some of them are for future degradation. So if you monitor some parameters, tell you whether the network is going south in a southbound direction, or if it is stable. So for those of you who attend, we're launching right now a poster. It's a reference poster. So if you are an expert already and you stayed for this presentation, I suggest that you probably send a link to those who are getting into PTP, because it can be daunting when you're reading all these white papers and presentations and you see all these acronyms. There is, again, no product placement on this poster. Is all reference, it's quick reference. So we made it for people on the field that if they want to know what FPP is, they can just look at the glossary that we have. If they need to find a standard, we have the QR code here. So make sure that you download the PDF of this presentation, which is right now if you're using an app, it's on the top. Little piece of paper, just click on it and download the PDF. So when you're, that will give you the link, or you can just go to our website and type packet network synchronization poster, and it will take you to the link to download the PDF, high quality. We will try to send this to as many people as we can. If you want a printed copy, we will send it to you. If you are outside of the US, we still send it to you. We don't know if you're gonna get it on time or ever get it. But if you really need it or you think that is valuable, the PDF is a very high resolution PDF, so you can print it locally if you want to and give it to people who needs it, who are getting into the PTP. And with that, I have to do my marketing, and then just, if you didn't know already, VX, we focus on field-oriented solutions for test and measurement, and that also applies for synchronization verification. And we thank you for staying with me a little bit longer than I was planning, or maybe not. So I'm gonna check if we have questions that we can answer, and I will stay for as long as we need to answer as many questions as possible. So maybe Mario or Ricardo can help me see if there are any questions. I don't see anything on the chat, and I don't see anything on the questions, so maybe some of them were answered. But anyways, if you have any questions, just email us and we will try to help you with whatever we can, whether it's information. We have YouTube. We have tons of videos about disciplining atomic clocks and GNSS information that probably can help you a little bit if you are coming into this field. Okay, Mario or Ricardo, do you see any questions or any questions that you responded that are worth answering live? Okay, so then thank you for staying. I hope you get something from it. At the very least, I just want to steer the discussion, start a discussion, and maybe you question your own methods and procedures, or how people are being trained to troubleshoot PTP. There are some companies who believe that their network is well engineered, so PTP is kind of plug and play, and that can be true. But in some cases, you will have to go troubleshooting when something goes south, and that's where we play is in the verification and troubleshooting of services. So thank you so much. And with that,